Today we are going to talk in detail about how to test an intelligent power module, known by its acronym in English as IPM, Intelligent Power Module. These devices are among the most important elements in modern power electronics, and their use has expanded enormously in recent years. They are found in air conditioning equipment, inverter refrigeration systems, variable speed drives for electric motors, pumping systems, inverter compressors, and even in high-efficiency household appliances. In general, any application that requires precise, reliable, and efficient control of three-phase electric motors makes use of IPM modules. The main function of an IPM is to integrate into a single package several IGBTs, insulated gate bipolar transistors, along with freewheeling diodes and internal protection circuits. This integration makes it possible to handle high currents and voltages efficiently and in a compact format. Thanks to this, they greatly outperform older systems that relied on discrete transistors, which took up more space, generated more heat, and were less reliable. Among their advantages, we can highlight simplification of PCB design, since the number of external components is reduced. Greater system reliability by incorporating internal protections against abnormal conditions. Lower energy losses resulting in higher efficiency. Better heat dissipation by concentrating the power elements in a single optimized structure. Under normal conditions, the IPM receives high voltage direct current from the board's power supply, and its mission is to transform it into three-phase current with variable voltage and frequency. This allows precise control of the inverter compressor motor's rotation speed, adjusting its performance to real demand and reducing energy consumption. In addition to IGBTs, many models include internal protections against overcurrent when more current flows than the system can handle, overtemperature when heat dissipation fails or the module operates under extreme conditions, undervoltage or overvoltage which may be due to instability in the power grid. These protections reduce the risk that an external anomaly immediately damages the rest of the system. However, when an IPM fails, it almost always does so abruptly and catastrophically, generating severe short circuits that can compromise the entire electronic board. In fact, in several brands of inverter air conditioners, error codes P0, P2, F2, F5, or H5, depending on the manufacturer, are often directly related to power module failures. That is why diagnosing the state of the IPM precisely is vital, not only to determine whether the board should be repaired or replaced, but also to avoid further damage to critical components such as the inverter compressor, the power supply, or the tracks of the electronic board. An undetected faulty IPM can leave a system completely out of service. Pin identification. Before starting any test, it is essential to correctly identify the module's pins. The most recommended way is to search online for the reference number printed on the IPM casing, where the manufacturer's datasheets can be found. If the number is not visible or has worn off over time, a practical check can be done with the board disconnected from the power supply. Locate the thick pins that have continuity with the compressor wires. These correspond to the U, V, and W phases. To identify the positive and negative power supply pins, use a multimeter and check which ones have continuity with the board's high-voltage DC input. Once the pins are identified, we can apply the four main test methods. First method, physical inspection. Always begin with a visual and tactile inspection of the module, since many times the damage is evident even before electrical measurements are made. Points to check: cracks, burns, partial explosions, or discolorations, clear signs of failure. Deformation of the copper base. Excessive heat can warp the metal base, revealing internal damage even if the top looks normal. Apparently intact casing. Sometimes the heat sink covers the damage, which is only visible at the base. Resin residue. Carbon traces or marks on the terminals often indicate internal short circuits. It is essential to check the thermal dissipation system. The heatsink must be clean and firmly in contact with the module. The thermal paste between the IPM and the heatsink must not be dry or cracked, and if it is, it must be removed and replaced with a new uniform layer of paste specifically designed for power electronics. Poor thermal contact is one of the most common causes of recurring failures in power modules. Second method, test with the board unpowered. For this procedure, a multimeter in diode mode is used to check the behavior of the internal diodes and IGBTs. When the IPM remains mounted on the board, it is mandatory to discharge the capacitors before testing. These components often retain dangerous electric charge even when the board is no longer connected to the power grid. Safe procedure to discharge capacitors. Use a 10 kiloohm to 100 kiloohm 5-watt resistor, connected to the capacitor terminals using wires with clips. Keep the connection for 20 to 30 seconds. Verify with a multimeter in DC mode that the voltage has dropped to 0 volts or close. Once the PCB is discharged, with the multimeter in diode mode, carry out the following checks. General steps. Set the multimeter to diode mode. Place the black probe on the common terminal and the red probe on the positive. Test the negative pins and phases U, V, and W. There should be no reading. Reverse the probe's polarity. Typical voltage drop should appear, around 0.813 volts between negative and positive. Keep the black probe fixed and test with the red probe on U, V, and W. All values obtained should be very similar. In some modules, values close to 0.412 volts are obtained. If any pin shows 0 volts or values that are too low, it indicates an internal short circuit or leakage. The module is damaged. Now, reverse the probes. Leave the red probe on the IPM negative pin and place the black probe on U, V, and W. The readings should be very similar in all three measurements. In some electronic modules, you may expect values between 0.412 and 0.485 volts. If all readings are consistent, the IPM is in good condition without needing to remove it from the board. Fourth method, test with the PCB energized. This is the most conclusive method, but also the riskiest, since it involves working with voltages up to 300 to 320 VDC. It must be carried out with extreme caution and only by personnel experienced in power electronics. Typical tests. Measure between positive and negative. It should be between 300 and 320 VDC. On U, V, and W, values between 10 and 15 VDC should be recorded, stabilizing around 11.7 volts depending on the manufacturer. Characteristic failure case. An IPM may pass visual and multimeter tests, but when the PCB is powered, the fault becomes evident. For example, if on phase V, instead of approximately 12 volts, 304 volts appears, it means the IGBT of that phase is short-circuited. In such a case, the only solution is to replace the entire module, since the damage is irreversible. With these complementary methods, it is possible to perform a complete diagnosis of an IPM from preliminary inspection to final verification under real working conditions. Knowing and applying these tests is essential to ensure effective repairs and avoid recurring failures in modern inverter systems.